Hello everyone, welcome to my webcast video. In this webcast video, I will show you how to derive the OLS formula. So OLS formula is the most basic formula in econometrics. So OLS formula means ordinary least squares. And the formula looks like x transpose x inverse x transpose times y. So in the OLS we have a linear model. So y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus x beta k minus 1 x k minus 1 plus epsilon. And this can be written as with x transpose beta plus epsilon. So x vector is starting with 1 and x1 and xk minus 1. And beta vector is start with beta 0 and beta 1 and beta k minus 1. So both vectors are k dimensions, so k by 1 and k by 1. So this y is called dependent variable. And this beta 0 is called constant. And x1 and x2 and xk, these are called explanatory variables, or sometimes it's called independent variable. And this epsilon is called adder. So we have in this part we have one constant and k minus 1 explanatory variables. So now what I'm gonna do is to explaining how this big X and Y metrics look like. So let's go to a new page. So we have n observations, and the index for observation is I, and this is of course from 1 to n. So the first observation would look like beta 0 plus beta 1 x11. By the way, this means the first explanatory variable of the first observation, and plus beta 2 x21, of course 1 2. So this is the second explanatory variable of the first observation, and beta 3 x13 and so on, and beta k minus 1 x1 k minus 1 plus epsilon 1. And the second observation is beta 0 plus beta 1 x21 plus beta 2 x22 plus beta 3 x23 plus beta k minus 1 x 2k minus 1 plus epsilon 2. And we have nth observations. So the nth observation would look like yn equals beta 0, beta 1 x n 1 plus beta 2 x n 2 plus beta 3 x n 3 plus beta k minus 1 x n k minus 1 plus epsilon n. So what I want to do, make these n observations into these n observations into a matrix and vector notation. So this can be written as the first, the dependent variable y1, dependent variable vector y2, and yn. And this X matrix can be written as 1 times x 1 1 x 1 2 x 1 k minus 1 1 x 2 1 x 2 2 x 2 k minus 1 1 x n minus 1 x n 2 x n k minus 1. And here we have parameter vector, beta vectors, so beta 0, beta 1, and beta k minus 1. Plus we have also adder vectors, so the first adder, the second adder, until the nth adder. So let's check the dimensions. So this is n by 1 vector, and this is n by k matrix. And it's quite interesting that this the first column of this matrix is always a vector of ones. And this beta vector is k by 1, and this epsilon vector is m by 1. So in the end, this left hand side is m by 1, and the right hand side is also m by 1. So everything is perfect. So now, from now on, I will call this vector as y, and this one I will call x, so big X, capital X, and this I will call beta, and I will call this epsilon. So from this time, the notation becomes a bit different compared to the previous slide. So y is a m by 1 vector, and x is m by k matrix, and beta is k by 1 vector, and epsilon is m by 1 vector. So keep in mind that. So now we have a model y equals x beta plus epsilon, and as I already said, this is m by 1 and m by k, and this is k by 1, and this is m by 1. So to find the OLS formula, so our aim is to derive this formula. So So to derive this formula, we first have to define the loss function. And in the OLS, we did not, our loss function is always epsilon transpose epsilon. So I will call this function as L, and this is equal to the summation from 1 to n epsilon I squared. Or of course we can just write y minus x beta transpose times y minus x beta. This comes from here. So epsilon is equal to y minus x beta. So what I'm gonna do is differentiating. So I will first find the derivative of this loss function with respect to beta, and then find the point where the derivative is equal to 0. I will differentiate the loss function with respect to beta, and I think before doing differentiation, I think it's good to spread this loss function out first. So this guy is equal to y transpose x beta transpose x transpose times y minus x beta, and this is equal to y transpose y minus beta transpose x transpose y. Y transpose x beta minus beta transpose x transpose y plus beta transpose x beta. And you should know that this guy and this guy are actually the same, because the dimension of the loss function is 1 by 1, which is scalar. So when you transpose a scalar, then it is equivalent to the scalar. So if you transpose this guy, then it becomes beta transpose x transpose y, which is also equal to this guy. So I can actually write these whole things as 2 times beta transpose x transpose y plus beta transpose x beta. So I'm gonna differentiate this. So first, if you differentiate this term by beta, then this becomes 0 because there's no beta in this term, and this don't worry, don't be scared too much about vector differentiation. This is nothing. This is just nothing different from scalar differentiation. So we have one beta here. So if you differentiate this thing with beta, then it just become minus 2 times x transpose y. And this is, we have 2 beta. So if I write this as like a scalar, let's say this is not a vector and matrix, it's just number, then it is just equal to this. So if you differentiate this by beta, then this becomes x squared beta, right? So if you differentiate this part, then this becomes 2 times x transpose x beta. and I want to find beta that makes these things equal to 0. And this is equal to x transpose x beta equals x transpose y. And if you multiply x transpose x inverse, then beta equals x transpose x inverse times x transpose y. And this is called OLS formula. So we have derived the OLS formula. So, but one thing I want to mention is before differentiating, we have to know this loss function is convex. So convex means looks like this. So I simplified too much, but let's assume we have 2 dimensions. Then if we find the point where the derivative becomes 0, then we are sure that this is the minimum point, right? So I want the loss function to be look like this. So this is convex, and is this function convex? And my answer is yes, it is convex. So actually there are 2 ways to prove this function is convex. So I will just briefly mention how to prove it. So the first way to prove the convexity, so convexity of loss function is the first way is to find Hessian. So Hessian is you differentiate the loss function with respect to beta and beta transpose. So Hessian is equal to double differentiation with respect to beta and beta transpose. And if this is positive semi-definite, then this means that convex. L is convex. Loss function is convex. So this is quite a bit difficult actually. So there is some more intuitive way. So we have proposition. So any square of linear functions is convex. So in vector notation, y minus x beta is a linear function, and y minus x beta transpose y minus x beta is a square of the linear function in matrix notation. That means this is convex. If you don't understand, then just try with any just a simple linear function in Scala. So for example, minus 2x plus 1 squared. If you draw this function, then this would look like this. So it's convex. So it's always the case. So you can be sure that this function is convex, and you can feel pretty free to differentiate the loss function. So okay, thank you for watching, and we have derived the OLS formula.